Hey folks, welcome to our second ever AP Chemistry podcast. This is Miss Gray, and joining me today is the lovely Shannon Mast.
Hi.
Yep, that's her whole entire greeting. Hi.
I worked so hard on that greeting.
Yeah, there you go. So we're going to work on electrochemistry today, and since this is a new topic for us, you've got a new problem set to try. Yay! We will probably not do all of these. This is just what I had from last year. So we'll cross off some of these in class. You got to come to class to find out which ones. How's that sound?
That sounds fair.
All right, very good. So these are your problem sets, and then these are the objectives of the things that we'd like to accomplish today. We want to explain the difference between an electrochemical cell and a voltaic cell, and identify the function of the components of an electrochemical cell. We're going to learn how to write standard cell notation of a reaction that takes place in an electrochemical cell. Construct a redox reaction from cell notation. I know we can do redox, but we haven't learned what standard cell notation is yet. And then we're going to learn some new terms: electromotive force, cell potential, and cell voltage, and standard reduction potential. So we're going to do some new things that we haven't ever done before. But before we do, let's start off with some old things. Remember oxidation numbers, Shannon?
Yes.
Good, because we need to do those here. We got to figure this out. So here's what we do. We know that nitric acid, HNO3, has an overall charge of 0, right?
Yes.
Because it's a compound.
Of course.
Right. And molecules don't have charges. So what's the charge of the hydrogen?
Positive.
How much positive?
1.
Yeah, plus 1.
Okay.
And we know what the charge of the oxygen is. What's the charge of one oxygen? Negative 2. Right. And how many of them do we have? 3. And we have to add up to 0, right? So what's the charge of the nitrogen going to be? We'll call it X for now. We know that we have 1 plus a negative 6 plus X. And that's going to equal 0. So we're solving for X now. So what do you think is X?
5. Oh wait.
Positive or negative?
Positive.
Yep.
Good.
Positive 5. So X represented the oxidation state of nitrogen. So I have a plus 1 here, and a minus 2, and a plus 5 for each of the substances in nitric acid. Yeah, that's all we're doing.
Good.
Okay. So what if we had nitrous acid? Then hydrogen's going to be the same, positive 1. Positive 1. Gosh, this pen. And then nitrogen we'll call the X. And then oxygen is our minus 2. And there's 2 of them. Why did I put the hydrogen in here?
I was enjoying the hydrogen.
Oh, sorry.
Oh.
You'll have to enjoy that later. All right. So now, what's the charge of nitrogen going to be?
4.
Wait, let's see. I have 1 plus negative 4.
Just kidding.
Yeah.
It's a good thing I didn't do that in my head at all.
Equals 0. Yeah, so
3.
you tried that again. 3 plus 3.
Good, good.
And when we change nitric to nitrous, its oxidation state changes. Not the oxygen or the hydrogen, but just the nitrogen. So we know which substance is reduced, which is oxidized, because we can see to go from a 5 to a 3, we had to gain electrons. And because 2 of them, right? And because Leo says Gur, we know that the gain of electrons is reduction.
Of course.
Right. The loss of electrons.
Oxidization.
Oxidization.
Leo.
Yeah, Leo.
Yeah.
Yeah, that's the Leo part. Now let's do something more complicated.
Okay.
Lead sulfate. Because I'm not sure which kind of lead this is yet. We're going to have to look at the charge of sulfate. Overall, the charge of sulfate is
2.
a 2
Negative.
minus.
Of
right?
course.
And now we know which kind of lead we have.
We have the plus right?
Ooh, fancy. Going back to
What?
classical naming system. That would be for all those who use that naming lead 2 rather than the lead 1.
It's a Bud Light.
Yeah, but the lower of the two charges has the indigas and Shannon is a beast, I think. So we have lead 2. Oh, come on, Ken. Here we go. Lead 2. And that's combined with sulfate. So sulfur and oxygen we already know is a 2 minus. And there's 4 of them. So here on this side we've got 2 plus X. And how many oxygens?
Yeah, 4 of them.
Okay, let's just multiply that out. Then 4 times 2. Oh, it's a negative 8. I'm watching my signs. Don't mess that up. So what will we call X then? 6?
I got 6. That's me personally.
All right, is it positive 6 or negative?
There's a positive 6.
Yep. So in sulfate, the charge of the sulfur, or the oxidation speed, we should say, is a plus 6. So we could keep going, Shannon, and we can do a couple more, but I think we got this.
I think
Right?
this is on like Donkey Kong.
Right. So even if there's a whole lot of atoms in something, we just do one thing at a time. Yeah.
True story.
Yeah, don't make it harder than it needs to be, guys. Yeah, I think you've heard me say that before.
Oh yeah.
Yeah, I would like how my writing is so good. So wait.
I rather enjoyed it.
Yeah. All right then, let's be real. Acidic solution.
Amanda Lindsay style. Be real.
And this is our infamous redox reaction. If we're going to talk about electrochemical cells, we are going to be balancing redox reaction. And the first time we learned this, it seemed so complicated. But now that you've had some experience, it's going to seem a lot easier this time. I
That's true.
promise.
Okay, it better be.
Yeah. Well, just in case you haven't memorized everything that happens with reduction and oxidation, I gave you that sheet that says, what does it say? Stuff I should know for the APE test, but do not know yet. Well, a lot of those things that say you don't know them yet, you already do know them by now. But we got it out just in case. So we've been talking all this time so that your classmates can go find theirs, in case they need it.
Of course,
The-
cushion.
Right.
Good.
Yes, it's that paper that says stuff I should know. Go find that one. Right now.
Pause this.
Hit
Can't
pause on
even
the podcast.
continue.
Okay, so when we do redox, we have to do the reduction equation and the oxidation equation. We call these half reactions. Every time you balance redox, please start with the half reaction. So what happened to aluminum in this reaction?
It lost.
It lost electrons?
Yeah.
Okay, so I cleared out my writing because I just remembered if we're going to do redox, we have to do all of our half reactions in the middle. Start in the middle so we can add stuff. So it lost electrons. So we separated them. The electrons are now part of the product. Agreed?
Agreed.
We took them away from where they were. Now they're separated. And now we have permanganate. That was probably something like potassium permanganate. Remember we did a titration with that stuff? So what happened to our potassium in this situation? Why didn't we write it in here?
Wait, what?
If this was potassium permanganate before,
Oh, because it's the naconosa. Nobody wants to hang out with potassium.
totally, it's like this. Doesn't
no
hurt.
friends.
Has no friends. No one wants to hang out with that guy. So potassium just goes away. Anytime we see potassium in our ionic equations, we tend to just drop them out because no one wants to hang out with that guy. Can't talk. Okay, so look at your sheet and tell me what happens to permanganate in acidic solution.
Got this. Mn turns into 2 plus.
Mm-hmm.
It loses 2 electrons, and then water,
Oh, why water?
because we have the oxygen.
Yeah, we've got to figure out that oxygen thing, right? So where did the oxygens go? We can turn them into water.
Of course.
How many waters do you want here?
Well, we need 4 since we have
4.
4. Of course, look at that.
Good. But now I've added hydrogen to the product side.
So you need to add 8 hydrogen ions.
There you go.
Oh, good
Ooh.
life.
Fancy words. Ions.
ions.
So they better be charged particles.
Of course.
Okay, we have one more thing to put in here. The oxidation state. That permanganate is going to determine how many electrons were transferred. So we just did oxidation states. Permanganate has a -1 charge overall. So we're going to add up to -1. We have 4 oxygens, so that's a -8. And we got to figure out what the manganese was here.
It's 7.
+7 or -7?
+7.
Okay.
Because it's cat, and then cations are positive.
Yeah, definitely. And metals are usually positive, right?
Of course.
Yeah.
The metal.
Yeah. So now that we know how many the charges are, how much, whatever, yeah. +7 to +2, how many electrons had to be transferred?
5. Got this.
Right. Do we put them on the product side or the reactant side?
The products.
Because we're gaining an electron?
Yes.
Well, if one thing lost electrons...
I was just kidding. I was testing you, Mister.
Oh, no, you said it correctly.
Good.
Gained the electrons. So we put them on the reactant side. And remember, aluminum lost electrons?
Of course.
You can't have both things.
Okay, yeah.
So we put these ones over here, and that was the right place for them to go. Our other ones have to go on the other side. So now I need an eraser. Because I don't want this in my way. Oh, hey, eraser. Yeah, oh well. My students are used to seeing me on something like that.
Bye-bye.
Yep, let's go back to our pen. Our green pen, so we can see it, because I don't think black would show up very well there.
Oh, no. Well, we could. I mean, just have to squint.
Yeah. Well, chemistry's hard enough. Let's not make it worse.
Good idea. Good.
Okay, now how do we combine our 2 half reactions?
Oh, yeah. You have to balance each electron.
Right, we gotta be able to cancel the electrons.
Yeah.
So how do I get 3 and 5 to be the same?
1, 5, each one. 5.
Like the least common multiple.
Exactly. So 5.
Okay, 5 here. And we're gonna multiply this by 5?
No, we multiply that by 3, so these.
Oh, me names. Game on.
Cute game.
All right, 5 aluminums makes 5 aluminum ions. Trying to write fast without messing up. G is 3 plus. And 15 electrons. Whoa. Oh, I pushed the clicker thing.
Good.
Back to pen now, let's see.
That was awesome.
I know, what the heck? 10. 15. And it's flat. I love it when things randomly change in the middle of a podcast. So exciting. 17 electrons. Okay, so the top one's done, right?
Of course.
Now the bottom one gets multiplied by 3. So don't let me mess this up. 14 and 24.
Yes.
I don't know why it does that. Are you getting a text message?
I'm not.
Oh,
I got
okay.
some really funny thing too.
Oops, I didn't put enough for manganate. And I'm not going to bother with the eraser.
Good.
5. No, 3.
3.
3.
That's a 3.
That is a 3. It looks just like a 3.
If anybody gets that wrong,
An S or a dollar sign. That's a 3, everybody. They'll figure it out. Are you making fun of me?
I would never make fun of Miss Ray.
No, never. That never happens in class all the time.
Only when people mess up the solution.
All right, squeezing the drops.
Oh yeah,
the
I
wells.
made everything pink and then life was good. It's so majority,
Right. So, now what?
And then you add them.
Okay,
Or
let's see
you
what
can
we'll
just
cancel
cancel.
first. I can't cancel any waters or anything else, just electrons, really. Right?
Nobody likes electrons.
Well, they're still there. They just have equal amounts. They better be balanced, or we've done something
They
wrong.
better be.
Okay, so I have 24 hydrogen ions and 5 aluminum. I gotta put the plus sign between them. 5 aluminum atoms. They are not charged particles, so they are not ions. And then I have 3. That was a 3. Yes.
Yeah.
3 ions of permanganate. Then on the other side, I'm left with 5 aluminum ions and 3 manganese ions. Would you call that manganic or manganese?
You would call that whatever you want to call it. Just life is.
I suppose it depends on what's the other kind of manganese, right?
Yeah, of course.
I think it's a B plus. We squishing that H2O. Hey, we did it all in one line. Redox reactions could be so long. Okay, well, before we did this podcast, I wrote down what the right answer should be. Would you check that? It's on that little half sheet of paper.
5 aluminum plus ions.
Okay, and
24 hydrogen plus ions.
Okay.
3 manganese ions.
Mm-hmm.
And then it forms 3 manganese plus charge.
Okay.
12 H2Os.
Okay, 12 waters.
And then 5 aluminum plus. Booyah!
Okay, but wait, you said them in a different order. So, did I get it wrong?
No, of course not.
No, I'm allowed to have it in a different order?
Of course.
I don't know what happened to our little arrows. So, yay, we did it right, but now we've got to be able to move on to the next slide. So, we're going to do some crazy manipulation to get our arrows back. Got it. See these ones? These are the ones I like. And these are those here. Those are the ones I don't like.
You don't like those.
I like these ones. Weird. Oh no, look, we got our redox reaction to balance again.
Yay! But we got
Oops.
the bag.
Wait, this one says it's an acidic solution. I beg to differ. You know what? I just typed this in and I typed it up. This reaction is going to take place in basic solution.
Of course.
And that means we're not adding any hydrogen ions in here. We're going to add hydroxides.
Of course.
All right, well, we can do this. So we start with half reactions. This one is magnesium, and the last time we did our half reaction in the middle. We're going to do that. Half reaction.
Don't even worry about that.
All right, magnesium in the middle. Come on, Ben, behave yourself. It's going to turn into magnesium hydroxide. Where in the world is the hydroxide?
It probably came from. Oh, well, it's in basic solution.
Right, exactly. So how many hydroxide ions should we put on this side?
2.
Good plan.
Good, good.
2 hydroxide ions. And then that's all balanced nicely.
Of course, look at this.
Right? Okay. Geez, am I doing it right here? I think I might be.
I think we're doing this.
Okay, now let's work with hypochlorite.
Yes.
Yes. Hypochlorite becomes chloride.
Yes.
All right. Now, what did we do in acidic solution when we had an extra oxygen that didn't show up on the other side?
We added water.
Right.
Or basic solution. So we add hydroxide.
Now we can add water.
We can add water?
Yeah, we just can't add.
Yes. Best day ever.
Yeah, we just can't add hydrogen ions. So,
Nobody wants hydrogen ions.
no, nope. So let's go ahead and add hydroxide if you need one. And then over here we have H2O to balance out the hydrogens. So I can't have just one hydroxide, right?
Right.
Because I have to get 2 hydrogens somewhere.
Good. I was right about to just ask that. Good thing you answered.
Yep. So are the oxygens okay?
Yep.
And the hydrogens are good?
Yep. So we're good.
All right. Well, I better put a plus in here.
That's a good idea.
Yep. Now let's keep track of our electrons.
Okay.
Because our equations have to be balanced by mass and by electrons. Oh gosh, we've got to go way back up to here and do oxidation of course. Magnesium hydroxide is a 0 overall.
Of course.
Okay, this is a 2 minus. We have hydrogen, and there's 2 of them. Each of them is worth 1, so we've got a 2 minus and a 2 plus.
Those cancel out.
Right? And so then what's magnesium?
0. Am I right?
I don't know, that's crazy. How's that possible?
Well, it's not a knock.
Oh, duh. Look, we have 2 oxygens too.
Oh, good.
See, it's a good thing we made a mistake so that we can teach humility here. It's an important thing to
Great
do.
thing.
Right. And this, oh, it's magnesium. What's the charge of magnesium? Normally is a +2.
Duh.
It doesn't have more than that. It's either a 0 in elemental form, or it's 2+.
Of course.
Okay, now we're rolling. We got this. So how many electrons were lost?
2.
2 electrons were lost to form the magnesium 2+ ion. All right, so we put them on that side. Now let's look at what was gained. In hypochlorite, we have a -1 overall charge.
Of course.
Well, we know this charge of chlorine is a -1. That's a no-brainer. But over here, we had oxygen, which is our 2-, combined with chlorine, we'll call it X. So let's solve for X, so we can figure out the charge of chlorine.
1.
Just a 1,
I think so.
is positive or negative?
It's positive. Good.
Better be.
Just making sure.
Yeah, okay. So if chlorine is a +1, and now it's a -1. So we had to go from this step to 0, and then another step over to -1.
So there's 2.
Yeah, 2 electrons. Oh, hey, look how nicely that works out, too. 2 electrons and 2 electrons. We don't have to multiply and stuff.
Good day.
Yay! All right, what else can we cancel?
The hydroxide.
Yep.
Good.
Out of here. So now we're just adding up our reaction. And I'm really hoping we end up with the same answer as what I wrote down before we got started. Magnesium and 1 water and 1 hypochlorite, which maybe came from bleach. Bleach is sodium hypochlorite. So you could get hypochlorite at your house. I put magnesium in it, and you can make a battery out of it, because this is how we make batteries with redox reactions. So,
That's always great.
go get your magnesium.
Go make some batteries.
Got some in your pantry or something? Probably not.
Nah.
All right. Did we get the right answer?
We did.
Nice. I like it when that happens.
I feel pretty accomplished right now.
Me too, because remember how hard it was to do redox before?
Right there sucked.
Yeah,
Really
this
bad.
wasn't so bad. Even the one in basic solution.
Pretty good.
We got
I
this.
feel pretty okay.
I think we can do this. Oh, okay. How about I clear the writing though before we do the next
Good,
page?
good.
Everything looks weird. Yeah, I'm getting better. Getting